Hello everyone. Today I want to talk about variance inflation factors, multicollinearity. I want to talk about the relation between some variables and use that relation to find the confidence intervals. So what is VIF? What is variance inflation factors? It shows us, it's a kind of measure of actually multicollinearity. And the multicollinearity itself is a correlation among independent variables. So correlation among independent variables. Within a multiple regression, when we are talking about multiple regression. If the total amount for each variable's VIF, which each explanatory variable's VIF is higher or maybe it's same higher certain value, or maybe it's same as the VIF for other variables. In those situations, we have to discard one of these variables before moving on to building a model. High multicollinearity cause a problem in a model for us, because imagine if two variables are explanatory variables are highly correlated. This correlation doesn't let us to understand the model based on the dependent variable. It doesn't let us to understand what is the effect of each of these variables on the dependent variable. Okay, so the VIF, as you see here, I wrote down, it's 1 divided by 1 minus r square. So if we increase the r square, the VIF will increase. So increase of r square causes increase of VIF. If r square is equal to 0, then there is no multicollinearity because VIF becomes 1. Okay, so I'm going to copy paste this here for you. Okay, so now that imagine we know what's the relation between r square and VIF, and we know that VIF equal 1 represent no multicollinearity, means we like that. We want to see no multicollinearity between variables, and higher values of VIF actually shows more multicollinearity in the model. So we are always looking for lower VIF. Okay, so I will start with the data set I have. I'm going to import NumPy as NP, and I need pandas, and I don't draw a graph today, but still let's have all these important packages. Let me copy paste all these important packages here that we may use, and we are going to copy the path to the data set, and let's see what we have in this data set if you don't remember. So we have all the information about some serials. These are the name of serials. This is our index name of serial, and then we have some column: type of serial, hot or cold, calories, protein, fat, rating, all of these. Okay, so I'm going to create a data frame of my independent variables. So I'm creating a variable that will contain part of the data set. So the first argument in this bracket shows I'm choosing all the rows, and then the second argument I'm choosing an array. I'm choosing fiber, I'm choosing sugar, I'm choosing carb, I'm choosing fat. So these are the columns that I want to choose. Choosing part of data set, all the rows, and only 4 columns. Okay, so these are the independent variables for us. What did I do wrong again? Let's read it. It says passing list like to LOC with any missing label is no longer supported. Okay, so that's going to be, let's see. Well, I will keep this as a participation point. I don't want to fix it in front of you, but I will fix it later. So in this lecture, I can use these independence. So there is something very simple after I look through my code. There's a really simple thing that's a participation point for you. How can I fix this? Okay. Send me your answer, please. Okay, so here is the independent variable that I selected, all the 4 columns I needed, and it shows all the rows for the serial's name. Okay, so this is my explanatory variables. Okay, so now what I want to do, I want to use a method from stat models dot stats dot outliers dot actually underline influence. Then I'm going to import variance underline inflation underline, such a huge name. So I'm extracting this method from this library. No module stat. Did I even import a stat? I don't think I import a stat. Let me import a stat models. Okay, here it is. I had a multiple typo. Okay, so now I'm going to create a data frame VIF using Panda data frame, and creating data frame using pandas. And what I'm going to do, actually I want to see some of the characteristic of this independence like shape. So we have 77 rows, And then I want to know the values. These are all the values for all the variables, all the 4 columns without the column name, without anything else. And then all values without columns name. So what I'm going to do here, I'm going to show you another attribute of the data frame we have. This shows all the index, shows all the index or name of the columns. Okay, so the reason I'm showing you, because in next part I'm going to use some of this. So I'm going to create a column named VIF factor in the VIF data frame, and then I'm going to use variance inflation factor of each of these independent values, and then I'm going to create a loop which says for I in range, what is the range? Range will be shape index 1 of shape. So look at the shape. Shape was 77 and 4, right? And 4 columns, correct? So when I say independent shape index 1, I mean I am extracting this value 4. So what it says for I in range of 0 to 4, I mean for 4 count, it's going to calculate the VIF in each of the column. Means it's going to go through all the values we have and create VIF for each of these columns. So for 4 columns, it's going to create VIF for each of these columns for us. Okay, so this is going to be VIF factor. And then we have another part of this data frame. I'm going to create features, and the features are going to be independent columns. So let's see what we did. We are going to print VIF, and now you will see the VIF is this matrix form, which has a column of factors, VIF factor, and then other column is the name of each column. Okay, so what I'm going to do now, you know why I showed shape, why I showed values, why I showed column. I'm going to comment them out. So we are just going to keep these, and then you are going to see VIF. So what I'm going to do, I'm going to round the values of VIF to 2 digits after decimal. Okay, so this is the VIF values. If I don't use print, let's see what I get. This is more beautiful. this table is more beautiful. Okay, so what we have, VIF for fiber is 1.56, for sugar is this much, for carb is this much, for fat is this much. If any of these were similar or any of these were higher than 5, we would suspect that there's a multicollinearity between the explanatory variables. In which model? What was our model? The Y was calorie, and all the 4 variables I'm showing here are the explanatory variables. Okay, so for example, let me explain this one. For example, let's say, okay, 2.7, oh, this one, 2.98 is 3, right? So I can say a VA of 3, for example, indicates that multicollinearity inflates the variance by a factor of 3 compared to a model with no multicollinearity at all. And to consider VIFs of 5 or more than that as a problematic amount of multicollinearity. And in that case, we had to remove or discard some of the variable and investigate further. Okay, so I have another participation point for you before I move forward to the confidence interval, concept of confidence interval. Okay, so participation point for, this is second one. Do you remember Boolean expressions we talked about? So now I want you to use Boolean expression to separate the calories, the values in the column that contains calories. So I want you to make 2 groups. I want you to create a column of data set that we have. This column, that when you write a code, when you print out the code, this column should show 2 columns. First column should show the name of cereal. The other column should show all the cereal that has a calorie above 100. And then I want you to write another code that the output of print of that code, the output will show the calories that are less than or equal 60 with the cereal name, right? So you will have 2 columns. The first column is showing the index, the name of cereal. The other column is going to show the calories for above 100 one time, and another time it's going to show the calories less than or equal to 60. So this is the second participation point you have for this lecture. So now we want to talk about confidence interval. So let's say you have information of public loan that the students in America owe. This will be whole population of students, right, as individuals. So students in this study I'm talking about are the individuals of a study. And then their student loan, the amount of a student loan will be the variable in the study. So then let's say I'm interested to know what is the average student loan in America. Then imagine in America there are lots of students with lots of student loan, right? It's very difficult for us to know how many students, what's the amount of a student loan, and then calculate all the information we want. But let's say average student loan that comes from the population, obviously it's unknown because there are so many students in America. So now, how can I estimate this without knowing the information of population? I can estimate this by finding the average of a student loan in a random sample that I get from the population. And always we should be careful. This random sample that I'm talking about should be very reasonable. The sample size, the method you are choosing this sample. If everything is correct, whatever information this sample is giving me can be an inference of the population information. It can estimate population information. So, okay, now using the information of sample and the information of sample, let me write down, using the information of sample, and we call the information of sample a statistic. We can estimate or predict the information of the population, and we call this parameters. So look, parameter has P for population, sample has S for statistic. Both of them has S. Okay, so I'm going to use the information of population to estimate information of sample to estimate the information of population, right? This is a concept of statistical inference. So this is called inferential, actually, statistics. Why? Because we are making prediction from a sample. Okay, so confidence interval is one of the methods that helps us to estimate the parameters. And what are the parameters? Parameters can be mean of population, we show that with mu. I will show you, actually later I will show you this symbol for population. Okay, so we can use the information of a statistic like mean of sample, which is x bar, to give an estimate or prediction about the population information. As I said, for example, mean of population, mu. Okay, so CI, or confidence interval, is a range that range of value derived from sample statistics, like, as I mentioned, x bar. And it's likely to contain the value of an unknown parameter. This is the unknown parameter of population, like mu. So CI is a range of values derived from sample statistics, and it's likely to have the value of an unknown population parameter. If you repeat sampling many times, then you are able to capture the population mean, for example, parameter, any parameters of population, within a certain confidence level. So when I say confidence level, we show that with C. The most typical one is 95%. Also, we have like 90% or 97%. But this is the most typical. 95% is most typical. Like the way I said, alpha equals 0.5 is the most typical. Okay, so we can use CI to compare actually different population. We can find or estimate the parameter of population. We can also compare different groups in the population. We are going to go through examples of this and see what exactly we can do with confidence interval. And remember, always, if your sample size is large enough, means 30 or more, we don't have to follow a certain assumption for our data set. We don't have to have, for example, a normally distributed data set. As long as we have enough sample size, 30 or more is enough sample size. The more better, right? Do you remember the law of large number? Okay, so CI or confidence interval can be calculated for the mean of population mu or the proportion in the population. We will start with the CI for the proportion, then we talk about the mean. So now actually I have some information here. So this one I wanted to show you, this one, and this one. Okay, so first of all, let's look at this. So when I said a statistic is like X bar. X bar is a statistic. Why? Because it comes from sample. Then whatever comes from population will be the parameter. Mu, which we show like this, is the mean of population. X bar is the mean of sample. So small n is the sample size. Capital N is a population size. So we can use a statistic, which is the mean of sample, to estimate the mean of population. This one. Okay, so this is the formula for confidence interval for the mean of population. So we use the mean of sample, we use the statistic, we use a standard deviation, we use sample size. X bar plus and minus z multiply s over square root of n. The first part is estimate, comes from sample. The second part, which is this one, is the standard error multiply the statistic, test the statistic. Sometimes test statistic can be t, sometimes can be z. It just depends on what information we have and what is the sample size. If our sample size is above 30, we can use z, this one. If our sample size is less than 30, we must use t distribution. Okay, so this part is the margin of error. Margin of error. Margin of error has an indirect relation with sample size, has a direct relation with z, has direct relation with standard deviation. So estimate plus minus margin of error. When we say estimate minus margin of error, we talk about lower bound. When we say estimate plus margin of error, we talk about the upper bound of confidence interval. So confidence interval is a range of value. We find a lower bound, we find an upper bound. And this confidence interval, you see, finds the boundary for the population mean mu here. So this top part, confidence interval, finds a boundary for population mean mu. So it says the mean, population mean, will fall between a lower bound and upper bound. So this one you see here is the confidence interval for the population proportion. So this proportion you see is a statistic. this statistic says, for example, what is the proportion of female who has a certain, for example, disease in a population, in a sample, and then these are all the same. This one, and this one. 1 minus P is the population proportion for those who doesn't have a disease, for example. And then Z is same as this one. Plus minus shows upper and lower boundary, and this will gives us the confidence interval for the population proportion. As example, I said the female who have a disease in population. We can give a proportion of female who has a disease in the population, in whole population, by using this estimate, by using this formula. Okay, so what is this one? What is this one? This one gives us information for the population mean difference. This one gives us the information for proportion difference. When I say difference, means imagine group 1, group 2, right? So for group 1 minus group 2, I can find the mean difference and say, okay, what's the mean difference of these two certain groups, for example, from the population? I can find the confidence interval for the mean difference. Here, using this formula, I can find the confidence interval for the proportion difference. So let's say this is the proportion of male who have disease. This is a proportion of female who have disease. I can find the difference of proportion using this formula, and I can estimate the proportion difference, proportion of population, difference of proportion population for female and male. Okay, we'll talk about that more when we approach that concept. Okay, so I'm going to show some basics that we need to find the some information. For example, I want to see I want to know what is the counts for some of the categorical variable in my study. I'm going to create a table, and do you remember Panda has a cross-tab attributes? So I can use that, say, okay, index of this table is dataset.mfr, which is one of the variables in the dataset, and the columns of this table is going to be dataset.type, and then I'm going to see what this table is giving me. So this table gave me two columns, cold cereal, hot cereal, and then MFR, which was a categorical variable for one of the columns of this data set. And then I'm going to, for example, do for another variables. Let's print this. These are just to give you information about the categorical variables you have in the study. So now I'm going to, one variable was data type, another was MFR, another is shelf. Shelf, yes. So look at this. Actually, let me print. And this is what I really don't like about Python or in general, Anaconda, Python, this kind of things. You must separate the outcome, and it doesn't create a kind of it doesn't print them in a next line with distance. We have to create separate them by one more line. Okay, so now look at this. Cold cereal that are in shelf 1, shelf 2, shelf 3, and then hot cereal. We have total of just 3 hot cereal in this data set. And then 19 of cold cereals are in shelf 1, 19 of them shelf 2, 36 of them in shelf 3. So I want to compare shelf 3 and shelf 1 and get a confidence interval first of all for the cold cereal in shelf 1, and then I want to get the confidence interval for the cold cereal in shelf 3, just as a kind of practice to know how we can how we can find some kind of confidence interval for some of the variables. So what I want to know now, again, I want to know what was the shape of the data set. Okay, so the shape of data set is 77. So remember, 77 rows and 15 columns. Okay, so now what I want to do, I want to say n is equal to 77. Or if I want to be more fancy, I can say dataset shape, and I want to get the index 0. Let's see what we get. N is 77, right? Because dataset shape had two index 0 and index 1, right? Index 0 is 77, index 1 is 15, correct? So n is dataset shape, index 0 means I'm extracting 77. So what is this? This is a total cereals we have in this data set, correct? Okay, so what I want to know, what is the number of cereal in a shelf 1, number of cold cereal in shelf 1. Look at this. It was 19, right? Cold cereal in shelf 1. And then let me print this. And then I want to know what is the standard deviation or standard error for cold cereal 1. What else I want to know? I want to know proportion of cold cereal in shelf 1. So proportion of cold cereal in shelf 1, and then I want to find standard error of cold cereal in shelf 1. Okay, so let's see what I'm talking about. S divided by square root of n is the standard error. So this is S. Oh, actually, sorry, I'm calculating this one, right? Proportion. I'm talking about proportion. So proportion multiply 1 minus proportion divided by n under square root gives me a standard error. So let's keep this on one side for us to see what we are talking about. Okay, so I want proportion of cereal 1. How can I find that? That will be the number of cereal, which is 19, correct, in shelf 1 actually, divide by the total number of cereal, which is n, right? So instead of 19, I could use this, correct? Because I already defined it. Number of cereal, number of cold cereal in shelf 1. This is the total cereal we have in the data set. So it will be n, correct? And then a standard error. How I find the standard error? This p hat you see here was the proportion of cold cereal in shelf 1. So I'm going to use this under a square root. Do you remember? NP_SQRT gives us a square root. And then this is the first p hat. I'm going to multiply this to 1 minus this proportion divided by what? This n here, please don't get confused, because here I mentioned, let me write down, this is n total. I don't want you to get confused and think that this n is the one in the formula. Okay, so this n here will be the number of cereal in shelf 1. So we have a standard error C1, right? And then what else I need? Z. Z for 95% confidence interval is 1.96. Just remember this. For 90%, I think it was 1.45. And then for 97%, it's 2 point something. 2 point something. So 2.5 something. So because mostly we are using 95%, you can memorize this, or you can just Google what is the Z value for 99% confidence interval. Let's Google it. What is the Z value for 90% confidence interval? 90% 1.64. What is 90%? 1.96. And then 99%. Did I say 97%? I meant 99%. 2.58, because these are the most important. 90, 95, and 99%. So these are all the Z value that you can find online for confidence interval. Okay, so let's go back now. Okay, so now we know the Z is 1.96, right, for 95% confidence interval. What I'm going to do here, I'm going to create this confidence interval. So I need the lower bound, I need the upper bound, and the lower bound is this proportion minus Z multiply the standard error. Proportion minus Z multiplies to standard error. Remember, NP SQRT, I already calculated the square root, right? And then what is the next one? Next one is plus. And then what I'm going to do, I'm going to print LB and UB. Okay, so this is the lower and upper confidence interval for the cereal that are in shelf 1. Okay, I hope I didn't have any mistake at all. NP squared T, Z is this one, Z multiply. Let me keep this in a parenthesis. So now you know that this part is the margin of error. Let me say what is the margin of error. margin of error is margin of error. Oops. Okay, so margin of error is 0.19. Okay, so this is the confidence interval. How can I interpret this? How do I interpret this? I will say we are 95% confident that we can capture the mean of, proportion of population for all the cold cereal in the market, in the shelf one, proportion of population for all the cold cereal in shelf 1 is between, we can capture the population proportion proportion of population for all the cold cereal in the shelf between this one and this one. So there are between this much proportion to this much proportion of the whole cereals are cold and in shelf 1 based on the information we have. Okay, so next time I will continue talking about confidence interval more, and we will talk about the confidence interval for the mean difference, and the rest of interesting things.